Okay. Good morning and welcome to lecture number 25. In the last lecture, we were looking at implementation of disjoint set data structure, basically to support three operations, which is make, find, and union. We assume that the sets being maintained are disjoint. So one assumption that we made was, so we assume in the beginning, so suppose there are n elements in the universe. So you have n single cardinality or singleton sets. Okay. So the make operation just ends there. So you just make n make calls and you have n sets. And the remainder of the operations are all either union or find. Okay. So yeah, so the idea was to store each link set as a linked list. And we store these elements in an array which also have pointers. So one pointer is parent, that is the pointer to the set which they belong to, that is to the linked list, head of the linked list. And we also have next pointer. Okay, so this is how it looks like implementation. So say we have two sets, S1 and S2. So this has head and tail. So head is the beginning and tail is the end. And then there are next pointers for each element. So you can assume that these are array elements. Okay, this is a structure array. And each of the element also points to the parent, that is the set to which it belongs to. Okay. So we saw find was fairly simple. So given x to find which set it belongs to, all we need to do is access the pointer x dot parent. X dot parent points to the set it belongs to. You either return the pointer, like I said, in applications where you also have a representative element for each set, that is, each set also has some representative element. So say some z1, z2, then you may have to have one more memory access, that is x dot parent dot the representative. Okay, so this is unit time operation, or you require order of one memory, many memory access. For union, so what we do is we just first apply find. So given x and y, so the idea is to unite or obtain a union of sets containing sx and containing x and y respectively, and replace the original sets by the union. Okay, so that is, we throw away the original sets. So all we do is we locate the sets containing sx and sy. So that is two find operations. And we locate the tail of the first list and then make it to point to the head of the second list, that is second set. And the tail of the second set should be set as the tail of the union. That is, for the new set, the tail will be the tail of the second set. Okay. Only thing is, now we need to update the parent pointers for each element in the second set. Okay, so for each item in sy, update the pointer, parent pointer to point to the head of sx. Okay, so yeah, so this is how it will look like. So when we take union of s1 and s2, so we just append the list s2 at the end of s1, that is here. Okay, so that is the tail, that is the last node, should point to the beginning of, or yeah, so the next of the tail should point to the beginning of s2. And now I update the tail to the end of the second. Only thing is, so here we need to update. So here update parent nodes. So towards the end of the last lecture, we saw that this could be the costliest operation. Okay, so in the worst case, you might force every union operation might be doing order of n many operations. Okay, so in the worst case, so we just saw one example, so let's say elements are x1 to xn. So we have make x1 etc. make xn. So then we call union x1 x2. I'm removing the set notation, union x2 x3. Oh sorry, the other way around. We always took the second set, right? x3 x2 union x4 x3, then union x5 x4 and so on, union xi plus 1 xi etc., union xn minus 1. Okay. So here the outcomes are singleton sets x1 etc. xn. Now here the outcome is set of cardinality 2. Here the outcome is set of cardinality 3 and so on. So what is the cost of this update operation, updating the parent? It is the size of the second set. Okay. So here the size of the second set, here it is 1, here it is 2, here it is 3, here it is 4, here it is I, here it is n minus 1. Okay. So the total cost unions is, apart from the find, which basically there are two finds, which is order 1. Okay. So order 1 into n plus the first one, it is 1, 2, again up to a constant factor, third one 3, etc., plus up to n minus 1. So this is order of n plus n into n minus 1 by 2. Okay, which is order of n square. So for this example, our implementation of union would require, in the worst case, so remember that we saw that since the sets are all disjoint, how many union operations are allowed in total?
n minus 1.
N minus 1. Yeah. So we saw that at most n minus 1 operations are allowed, right? So for this n minus 1 operation, so we came up with an example where it would force that we will spend a total of so many updates, that is order of n square many updates. Okay, so to be precise, n into n minus 1 by 2 many updates. Okay, so the total time complexity can be order of n square. So remember that there were n union operations. So this, by averaging, so this would be per union order of n. Okay, time, let's say. So in the worst case, we might be spending a time of order n updates per union. Okay, so together there can be at most n unions. So overall time could be order of n square. So if you assume that there are m operations, out of which at most n minus 1 can be union, so the worst case time complexity of the whole process could be order of n square. In fact, order of m plus order of n square. So remember that each find operation will take only order of 1 time. Okay, so this is order of 1 time. So this is the summary. Okay, so order of 1 for make set, find. So union, together it is order of n square in total, that is counting all n minus 1. See, it could be that you have smaller than n minus 1, but you just consider the worst case scenario. In that case, on an average per operation, it could be order of n. Okay. So, or in other words, if you use this for Kruskal's algorithm, right? So, what is our running time? So, implication to Kruskal's. So, what is the running time of Kruskal's algorithm? So, m log m is for sorting plus, so order of m, so the order will sit here when you find operations, right? So, m plus, so together the union operations will contribute order of n square. So, this is how it will be. Okay. So, this is possibly slightly better bound than order of mn that we had, but in particular when m is big, say m is order of n square, that is n choose 2. Okay, but still not much saving if you think about it. Particularly if m log m is less than n square, then this is expensive. Okay, but better than mn. So what was the earlier naive implementation bound? Order of m log m mn, right? Because for each of them you'll have to do a BFS to detect cycle and so on. So that, so we have saved particularly when the number of edges is larger than n or order of n. So it is say little omega of n, say n log n or n square or even n to the 3 by 2 and so on. Okay.
Hello,
but
sir.
not much. Yes. Yeah.
Sir, can you explain this? This thing is quite like a bit confusing to me. How is it order of n per operation?
No, that's what I'm saying. So how many operations have you done? N minus 1, right?
N minus 1.
Yeah. So I mean, see, when I say per operation, this is an average. So there could be operations which require only constant number of updates. But on an average, so because there are n minus 1 operations, so total will require order of n square. So per operation, it could be order of n.
Oh, simple division.
Yeah, that is all. We didn't do, I mean, no, it's a no-brainer. Yeah.
Okay.
Yeah. So, but we are not taking
Sir,
this
can you
on
please
an average thing. Yeah. Yeah.
can you please tell this factor of m in Kruskal's running time?
Which one? This one
Plus
or
m
this
is
one?
there, right?
Yeah. So how many find, right? So you'll have to traverse the edge list, right? So each will require 2 finds, right? When you're processing each edge.
Okay.
So that many
sir.
finds, but
Yeah.
the cost of unions is only this much. See, in the worst case, so if you take this as average and you say, okay, there are m union operations, then it will be mn. But if you notice, there are not, I mean, not more than n minus 1 union operations, and together they contribute this much. So that is why I didn't have mn here. Instead, I have n square. Okay. Yeah.
Okay, sir.
Sir,
Yes.
sir, in the previous, when you were trying to find the total cost of union, you took O of 1 dot n. So that O of 1 into n was for the make set operation of all x1 to xn.
No, no, no. So this is also no, no, no. We are talking about union only, right? Make set was done already, so I didn't include make set here. So this is for find. So you're making n unions, right? So each union will do finds, right? So this is one find, and see, union will be given 2 elements. So you'll have to locate the sets. So there will be
Yes,
so many finds. So this is the cost of find here.
yes, sir, thank you.
Find.
Hello.
Yes.
Sir, in the implication to Kruskal's, there we wrote m log m for sorting the edges. And
Exactly. Sorting. Yeah.
So I don't understand how did
Sorting
we
it.
write this n square? Okay, so we were doing on the vertices. Here n stands for vertices, and we are doing the disjoint set
Yes.
operations.
Yes. Yeah.
Then
So n number of vertices, n number of vertices, m number of edges. Yeah.
then the m factor, the plus m factor.
Yeah, so you are scanning each of the edge, right? So you will have to do find for each of them. So when you check if I union whatever edge EI is independent or not, that is acyclic or not. So that requires a find, right? In fact, two finds. So this is find. Because unlike here, so here the number of unions were n minus 1, hence number of finds were also n minus 1. Okay. Whereas in Kruskal's, you'll have to do so many finds, right? You'll have to scan through the edges. So you'll have edges E1 to EM. So for each edge, you are going to construct I union EI. So this requires a find, right? The whole process requires a find. Only thing is, you'll have, in effect, you'll have only n minus 1 union operations. Together, they will cost order of n square. So that's the only thing. So instead of m into n, so here it was like every time you are doing a BFS. So you'll require m into n. So that is disentangled. So m comes as a separate thing. So this is union. Is it fine?
Hello.
Yes.
Yes, sir. Okay. So it's just a bit confusing because here M is coming, and for each edge we are checking, we are doing find.
Yeah. So many finds have to be done, right? In the worst case, it is m. So it might be that you much earlier you would have constructed the spanning tree, but then you would stop if you had already n minus 1 edges. But otherwise, in the worst case, you may have to find for each of the edge, two finds for each of the edge,
For the
right?
cycle check.
Yeah, exactly.
Okay.
Okay, good. So now we are going to improve the implementation by a simple modification. Okay. So in fact, we'll make this as log n. So it's not exactly per operation, but per element it will be log n. So roughly overall, instead of n square, we'll improve it to n log n. So that's what we are going to do. Okay.
So,
Yes. Yeah.
sir, can you, yeah. Sir, we are, we are writing plus m for finding the number of ages. I mean, at the worst case, we have to find the age.
Yeah.
Sir, then we have to also check the cycle. So, in the asymptotic notation, the cost of checking the cycle will be
Yeah, that
written
is what, right? So when you have an edge, so for each edge, so for the endpoints, you will do find operation and see if it's the same tree, right? Or same set. That is the same linked list. So that is constant time operation, right? So if you have edges, say UV, how will you check for cycle? So find U, find V. So check if they are equal. Then cycle. Else no cycle. Right? So you basically require to find. That is incorporated here. So and each find will require constant many. So up to a constant multiple, it's going to be m. So it's not finding an edge. So for each edge, you'll have to do find operations to check for cycle, whether to include it in your constructed forest or not. Right?
Yes, sir.
Sir, but after performing this check, whether there is a cycle or not, then we are going to perform the union operation. Uh,
Yeah.
further.
So union together. Yeah. So union overall n minus 1, right? That is what that is accounted here already. See, union it's at most n minus 1 operation, and together they will cost order of n square in the worst case. So that is included here. So that union is we don't have to count separately. You're not
Sir,
going to
but
do more than n minus 1 union operations, right?
okay. Sir.
Yeah, there are some other costs. So make operation and so on. I'm just hiding them. So there is also plus whatever order of n for make operations and what else. That's it, right? Make operation. This is for make operation. You'll have to make n sets, right? So yeah, but that is subsumed by these values in the asymptotic notation. So yeah. Okay. Yeah. So now we'll suggest an improvement. Okay. So what was really painful thing here? Well, make was easy as well as find was easy. Union, the only painful was, so in this example itself, you'll have to traverse through one of the sets, all elements in one of the sets, right? And for the worst case example, so I just made it skew. The other side is huge. That is, the second set is huge. The first set is small. Then maybe you can say, what I'll do is what will be an obvious thing? Maybe I'll change sides. I'll do left first. That is, the first set will be attached to the right of the second set. In that case, you'll have to update only this much, right? Even then, I mean, if it is something fixed, that is, if you're either doing first or second fixed throughout, then I can always come up with a counterexample, right? The next improvement that you will think is maybe dynamically I'll think. So if I had swapped this somehow, if I could swap x1, x2 with x3, that is, I will append the list for x3 to the list for x2. Then this will be still one operation, right? So similarly, if I append the list for x4 to the list for x3, then this will be still one operation, right? So here there was a possibility to improve, if you think of it, right? But the only problem is dynamically, so all you have are linked lists. You may not know the size of the sets, right? Do I make sense?
We may, like, we can try to store the size in the S. That
Exactly. That's exactly what we are going to do. Okay. So what we can do is we can have an additional field here. So we'll store size here. So additionally, we'll store size. Okay. So that in such, so we will not be able to construct such skewed. So let's call this as skew, because one side is heavy, one side is light, right? So one side, the set is heavy, it has I elements, the other side has only one element. Okay. So such skewed scenario will not work. I mean, this will not be effective. Okay. So that is our improvement, or what we call as improvisation. Okay. So what we do is, for each set, store the number of elements in it. Now for the union operation, so we always update the pointers of the smaller set. That is, we'll be attaching the smaller set to the larger set. That is, appending the smaller set, that's linked list for the smaller set, to the larger set. So we'll always be updating the pointers of the smaller set. Okay. So that is all. Maybe I'll demonstrate here. Okay. So I mean, it's the same borrowed picture from CLRS. I just modified it a bit. That's all. Okay. So now what we have here is sizes stored. Okay. So this was the original picture, S1, S2, and their union. Now what we did is we stored sizes. So size of this set is 3, size of this set is 4. So when you do union, so you see that, okay, this is 3, smaller set. So now I'll append this set to the end of this. That is, this list is appended to the end of this. So I'll have CHEB coming first, CHEB coming first. Now this will be relabeled as S2. I mean, the same pointer here. Okay. Then I'll append FGD. So what is updates that I have to do? So I have to do updates here. So instead of 4, 3 updates. Okay. Is it clear to everyone? What is the change? So we have an additional field for each set structure. Okay. So along with head and tail, we also have size. At the initial make operations, each size will be set as 1. Okay. Now, at each union, how will you update the size? It's fairly easy, right? So you just add the sizes. So size becomes 4 plus 3, which is 7. But only thing is, we'll decide based on the size. So the smaller set will be appended towards the end, so that the update of parent pointer will be done for the smaller set, not for the larger set. So in this example, so if you go back to this example, so if you implement through this, right? So what will be the cost of each operation here?
One.
So each of the operation will be 1, right? So this is no more a worst case example. So what is the overall? So each of them will be replaced by 1 here. So this will be order of n, right? So we kind of easily have beaten this counter example. I mean, it's not clear if there are other counter examples, but at least this counter example we have worked through, right? So this idea easily beats it. This is no more a counter example. Okay. Yeah. So if there is any question, I'll take it now. Okay, so one quick question to everyone. So what do you think the improved bound would be? So can you think of a worst case example for this?
Both the sets are
So remember that, yeah.
equal size sets.
Equal size sets, okay. Yeah, that seems a good thought.
Both sets grow alternately. I mean, in one case, addition is done to one set, and in the second, to the other set.
I didn't get exactly. What do you mean alternately?
I mean, the sets are growing alternately. So, like, we have first we have only two sets. First, we have n sets. I mean, we can think
Yeah,
of two
first we
sets.
have n sets. Okay.
We can think of two sets as growing, say x1 and x2 in alternate steps. X1 is growing, and in the second step, x2 is growing.
Okay.
So that, like,
Yeah, but
in
that is
first
something that is something similar to what he said, right? Sizes are similar, and you're balancing the size. That's what you're saying, right?
yes.
Yeah. So okay, maybe okay. So I'll go for a blank slide here. Okay. Yeah. So.
Sir, it may so happen that multiple sets of same size can grow and then they converge to a single big set.
Yeah, that is what eventually happens, right? See, every union keeps on growing because the sets are disjoint. So that is why we said we can do at most n-1 unions, no more than that, right?
Okay.
So yeah, so anyway, the sizes are growing, but so let's just spend a couple of minutes on what would be the worst case example. So I'm coming to the first suggestion, which is like both sets are of equal size. That could be one bad example. Okay. So you have n sets to begin with. So what do we do? So keeping them equal means I'll take union of these two. So this will give me 1, 2. I'll take union of these two, 3, 4, and so on. So this is n minus 1 n. Then union of these two, which is 1, 2, 3, 4, and so on. This is n minus 3, n minus 2, n minus 1, n, and so on. Then again combine these two. In the end, you'll have, like you said, it's 1 to n. Okay. So let's just analyze this case. Okay, we are just trying to construct something. Let's see, is this the worst possible? See, what is it we want to do? We want to force our implementation to make to spend a lot of time. Okay, and how do we measure the time? So we'll come to that. Okay, so how do we? Okay, we measure the time per operation or together for n-1 operation. What is the total time? That is good enough for us. We don't have to say per operation how much. But what is the worst possible scenario for our implementation? So one suggestion was this. What is the time spent for this kind of sequence of operations? So is it clear what we said? So the union is basically first 1, 2, then 3, 4, etc. n-1 n, and then again 1, 3, and then what was that? 5 and what? 7, right? 5, 7, and so on. And then again 1 and 5, and so on. Okay, so these are the union operations. So I'll just write if you want. So union 1, 2. This is union 2, 3, and so on. Okay. So these are the sequence of union operations. So whichever sequence, it really does not matter. So together, this is how it should be. So the order, it could be, you can go this way. Maybe you cannot go this way because you'll have to build them. So you can go this way. So all of this, and then all of this, and then all of this, and then all of this. So how many union operations together? Precisely n-1, right? This is a complete binary tree, right? So assuming that, so let's say n is a power of 2 to simplify things. So then this will be n-1 operations. So we have exactly n-1 operations here. And yeah, in case when n is odd and so on, this will be a bit tough. So let's assume n is even or even a power of 2. Okay. So n-1 operation, what is the cost? Can you tell me the cost? Can you compute the cost here? Okay, is there some message? Wait a second, I'll check. N log n by 2. Okay, so why is that, Ritvik? What do you think it is?
Sir, we have total log n levels, and at each level we are doing n by 2 of movement.
Very good. Yeah, so it is slightly smaller than n by 2. So we'll see. N by 2. Okay, so you are saying total time spent is n by 2, right?
Yeah.
Yeah. Then it's right. Yeah. Okay. So at the bottommost level, so how many operations are there? Roughly n by 2, right? Not roughly. Assuming n is a power of 2, it is n by 2. Okay. So each of them, how many updates are we making? We are only counting the updates. Okay. So the pointer updates. So order 1 for each of them, right? So this time spent is order of n by 2. I'll just keep it as n by 2 here. Now, how many union operations at the next level? So remember, now there are n by 2 sets. So number of union operations will be n by 4, right? But what will be the cost of update for each of them? So let's say this is op, this is cost of updates, let's say. Sorry. Okay. So how many updates here? There was only one update per operation. So here, no matter what, the size of the set is going to be 2, right? So you'll have 2 updates per operation. At the next layer, it will be n by 8, and the size of the set will be 4. So there will be 4 updates and so on. Okay. So size of the set will be n by 2 power log n minus 1, and size of the sets will be n by 2, so updates will be n by 2. That's 2 power log n minus 1. Okay. Now if you add this up, so if you take, so all, what is the cost? You multiply this and add them up to a constant factor. This is the bound, right? What is it? At every stage, you are going to get n by 2, n by 2, n by 2, right? So that's exactly what Ritvik said. So n by 2, how many levels? Log n. So for this example, which one of you suggested as possibly worst case, the cost of updates, we are only looking at updates, we are not talking about find again up to so constant factor, it's order of n anyway, so no big deal. Okay, so it's going to be order of n log n. Yeah, so now the question is this the worst? So can there be worser examples? So see, when you suggested, right, so equal, both sets of equal size, that seems to be the bad case, right? Because if there is one smaller, then your number of updates is going to be smaller. So you can just imagine, so my gain, so you can just imagine, so from a set of size 1, I'm going to get a set of size 2. Okay, out of this size that I get, so at some level I am going to get a set of size k. What is the proportion of updates that I have to make? In the worst case, it is 50%, right? But in any other case, it's going to be less than 50%. So now if you just add them up, so for every set, you're going to make roughly, in the worst case, 50% of its cost. So that is what is happening here. Okay. So this 4 is basically 50% of the size. This is 50% of the size, 50% of the size. Okay. So this seems intuitively the worst case, and this also happens to be the worst case. In fact, we can prove that it is order of n log n. That's what we are going to do next. Okay, so we'll give a mathematical proof. Though intuitively this is what it looks like, but we need to argue it out. Yeah. So we have 1 or 2 minutes for quick questions, please. So remember that nothing else changes, right? Find, there is no effect in the cost. It's the same operation as before. Only union, there is a potential gain. In fact, once I prove this, the gain is significant. Instead of order of n square, we have n log n. Yeah, so this is just a description of the operation. So make, there is no change. Singleton set, and the size is set as 1. Find, there is no change. Union, it's the same. Only thing is you'll have to update the size. Okay. So the size has to be updated, and the pointer update will be for the smaller set always. Okay. Yeah. So this is what we are going to prove. So for the improvised implementation, union operations, how many of them? N minus 1 of them. At the max. In fact, it will be n minus 1 in most of the applications, particularly the Kruskal's algorithm. So total time taken is n log n. Okay. Okay, so we'll prove this formally. So what we do is we are going to count. So for each element, so let's say my set is 1 to n. So we will count the number of updates done to an element in 1 to n. So we prove that for each such x, at most order of log n many updates are possible. So you have n elements. For each element, I'm saying that you can do at most order of log n updates. See, remember that we are updating the pointer, right? So when I update the pointer for f, I'm accounting it for f. Okay. So this is added as a 1 update for f. This is added as 1 update for g, 1 update for d. So here there is no change in the updates of c, h, e, b. Okay. So that is how I'm going to measure it. In the end, we want to count total number of updates, right? That is our bottleneck, or that is a problem creator. So we needed order of n square in the original implementation. So now we are going to say that in this new implementation, overall there could be at most order of n log n updates. So the way we do it is any element can have at most order of log n many updates. Okay. So the claim is the following. So at any point of time, so x be any element, okay, 1 to n. If x has seen k updates so far, then x must be in a set size at least 2 power k. So do we see that this claim at once gives the required bound? It proves this statement. So what we are saying is that we are just watching out for element x here, okay, and we are just counting the updates made for that element. So if there are k updates made, the claim is it should be in a set whose size is at least 2 power k. Okay. So when I say updates, so we are discounting the updates that we make in the make set operation. Okay. So the make set operation we are not counting. Otherwise, this will be 2 to the power k minus 1. Okay. Yeah. Do I make sense? So this claim, does it imply our theorem? Yeah. So this statement implies the theorem immediately because there are at most n elements, or I mean exactly n elements. So we'll require a total number of updates will be order of n log n. Now the second claim basically says if an element has seen k updates so far, then it must be in a set of size at least 2 power k. But we know that the maximum possible set size is n, right? So 2 power k can be at most n. So in other words, k can be at most log n. So that this claim immediately implies this statement. So we are going to prove the claim now. Proof of the claim. So we'll do it by induction on k. Yeah, I'm assuming that there is no confusion so far. Else, please shoot in questions. Okay. So base case would be k equal to 1, or maybe 0. There is nothing to prove. K equal to 1. Okay. So this is we have seen one update. Okay. So let Sx be the set containing x, and y be such that Sx union Sy cost an update to x. Okay. So why did we make an update to x? So we updated x since cardinality of Sx is less than or equal to cardinality of Sy. Okay. But we know that Sx is at least 1, right? So therefore, cardinality of Sx union Sy, remember that the sets are disjoint, it's at least 2, which is 2 power k, k equal to 1. So therefore, after one update, to x, the set containing x has size at least 2. Okay. Oh, sorry, I don't have enough space, so that's fine. Yeah, does it make sense? Now for the induction step, so how do we do? So we assume up to k minus 1. Yeah. So consider the kth update. Kth update. Okay. So let the corresponding sets be Sx and Sy. So when we have Sx, so the number of updates must have been k minus 1, right? Yeah. So by induction hypothesis, by IH, size of Sx is at least 2 power k minus 1. Okay. So since x is being updated, so we have cardinality of Sy is at least cardinality of Sx, which is 2 power k minus 1. So therefore, cardinality of Sx union Sy should be at least 2 into 2 power k minus 1, which is 2 power k. So we're just looking at the last update, which is we call as kth update. By induction, when we have Sx, we should have seen k minus 1 updates, right? X must have seen k minus 1 updates because we are looking at the kth update. Kth update is via Sx union Sy. Okay. But by induction hypothesis, cardinality of Sx is at least 2 power k minus 1. But since X is being updated, that means cardinality of Sy should be more than cardinality of Sx, or at least as much. So which is at least 2 power k minus 1. Since they are being disjoint, their union will have cardinality twice the size of Sx, which is 2 power k minus 1. Hence, the new set that we got has size 2 power k. So the kth update for X will result in a set containing X has size at least 2 power k. This pretty much proves the claim. Okay. And which in turn proves our statement. So all we did is we just put a watch on each of the element. We looked at their updates. Okay. So if you made k updates to that element, then we are guaranteed that the set containing it should have at least 2 power k elements. And that pretty much proves it. It's basically a formal argument which kind of works in a very similar fashion. So this is the first update. So this is the second update. This is the third update, and so on. So in this case, what happens is the update is done only to this element here. I mean, one of them, not both the sides. Okay. Yeah. Okay. So this is the summary. So make set will cause, so per operation it will be order n, order on. So total will be order n. Find order 1 per operation, order m in total, because there will be m find operations, or that's the assumption that we made. So union order n log n time in total. Okay. So per operation roughly order of log n by just dividing by n. Okay. So overall the time will be order of m plus n log n, where m is the total number of operations, that is including find and union. The union together will cause only n log n up to a constant factor. Okay. Yeah. So Raghav, please stop recording. I'll stop here for today. If you have questions, please shoot in now. I'll be there till all of you leave.